A large electroscope is made with leaves that are 78 centimeters long with tiny 24-gram spheres at the ends. When charged, nearly all the charge resides on the spheres. Part A, which is the only part, says if the wires make a 26-degree angle with the vertical, as in the figure, what total charge Q must have been applied to the electroscope? Ignore the mass of the wires. Now that we've entered second semester physics, we find that we have a brand new force to deal with, and that is the electric force. Despite the fact that we have a brand new force, the methods by which one deals with forces have not changed since first semester physics. And so, the first step in every force problem is now, as it was then, to draw a free body diagram. I'm going to pick an object, and the object I'm going to pick is going to be the ball on the right-hand side. To complete our free body diagram, we must add to that dot an arrow for each and every force acting on this. We recognize that there will be a gravity force. 24 grams is 0.024 kilograms. So that mass times g is the weight of the small ball. Another force acting on this diagram will be the tension. Tensions always pull, and so it pulls along the string itself. And finally, the last force in question is the electric force. Because the two balls have the same sign of charge, the electric force will be repulsive, and therefore it will point exactly in the horizontal direction. The size of an electric force is K times the amount of each charge. Here, each charge is capital Q divided by 2. So I get capital Q over 2 times capital Q over 2 in the numerator. And then the denominator has the distance between these 2 point charges squared. We'll perform the calculation necessary to figure out that distance when the time is appropriate. For now, we recognize that this is a two-dimensional free body diagram. The object is not accelerating, and therefore we will set our coordinate system in whichever manner is most convenient. I find that a standard up-down coordinate system will be the best for approaching this problem. The convenience of this coordinate system is that two of our forces, the weight and the electric force, are already aligned with the coordinate system. Therefore, they will appear in only one equation each. However, the tension force needs to be broken into components, and to accomplish this, we begin our arrow following one of the axes, and we end with an arrow parallel to the other axis. We can immediately recognize in this diagram where the 26 degrees goes. It goes at the top of this triangle, meaning that the two sides are t sine of 26 across the bottom and t cosine of 26 along the edge. Now that all forces have been broken into components, we're ready to proceed in a completely normal manner, and I'm going to choose to analyze the y-coordinate first. I'll choose up as the plus direction for y, meaning that one of the two forces is t cos 26, and the other one in the minus direction is mg. Since there's no acceleration in the y direction, the sum of all forces in that direction is 0. Since there's only one unknown in this equation, we're able to solve it out very quickly, saying that the tension will be 0.024 g divided by the cosine of 26, which yields 0.262 newtons. Now that we have that result, we're ready to proceed with an analysis of the x direction. In x, I'm going to be choosing the positive direction to the left. It doesn't matter since there's no acceleration, and therefore the positive term is going to be t times the sine of 26, and the negative term comes from the electric force. As always, the sum of all forces in any direction is equal to the mass times the component of the acceleration in that direction. There's no acceleration, and so these forces also sum to 0. At this point in the analysis, we notice that there are two unknowns in this equation. Tension is known, however the charge is not, and neither is the radius r. Looking back at the figure, we remember that r is the distance between the 2 point charges, and so that's the bottom of this triangle. If we look to the right in this diagram, we'll see that this smaller right triangle, that includes the 78 centimeters as its hypotenuse, has a base which is half the radius. So we can therefore say that half The r, distance between the two particles, is going to be equal to the short side of this triangle, which is opposite to the 26 degrees, and therefore this is 0.78 meters times the sine of 26 degrees. We can solve that expression for r, which yields the result. R is twice 0.78 times the sine of 26, and therefore r is equal to 0.684 meters. Solving the previous expression for Q squared, we find tension times the sine of 26 times 4 times the radius squared over the electric constant K, which is 9 10 to the 9, and this yields the value 2.38 times 10 to the minus 11 coulombs squared. Taking the square root of that result, we have our final answer that tells us the charge is 4.88 times 10 to the minus 6 coulombs, which is the same thing as 4.88 microcoulombs.